Hello everyone, in this lesson we will continue to learn the time domain analysis module of continuous systems. Fifth, impulse response and step response. Let's take a look at the impulse response. It's defined like this. System under the action of unit and signal delta t, it produces a zero-state response. We call it impulse response. Note that there is a zero-state response. That is to say, the initial state of the system is zero. The impulse response is generally expressed as ht. For an nth-order system, it can be described by n-order differential equation. The left end of the equation is the response and derivative of each order. The highest order is n. The right end of the equation is excitation and its derivatives. The highest order is m. When the excitation signal delta t is substituted into the original equation, the zero-state response of the system under the action of impulse signal is ht. Then the system equation will be in the following form. With the mathematical model, let's look at the form of ht solution. Because delta t and its derivative are all zero when t is greater than or equal to 0 plus, the right end of the equation is zero, so the equation becomes homogeneous. So the form of this solution and homogeneous solution should be the same. Since it has the same form as the homogeneous solution, its solution must be related to the characteristic root. If the characteristic root is a single real root, then its solution has the following form. Secondly, the form of this solution is also the relative size of m and n. They are related. When n is greater than m, the order of left end is higher than that of right end. Then ht does not contain delta t and its derivatives. When n equals m, delta t shall be included in ht. And when n is less than m, the order of the left end of the equation is lower than that of the right end. In this case, ht should include delta t and its derivatives. After analyzing the form of ht solution, let's take a look at the specific solution process of ht. That is, the solution process of impulse response. We will discuss it in two cases. First, if the right end of the equation contains only the excitation ft, without its derivatives, then the differential equation of the impulse response of the system is like this. There is only one delta t at the right end of the equation, because impulse response is zero-state response. So the impulse response and its derivatives value are all zero when t is equal to 0. When the characteristic root of the equation is assumed to be a single root without multiple roots, the form of ht is shown in this equation, where ci is the undetermined coefficient. This undetermined coefficient is determined by the initial conditions, which is determined by the value of 0 plus. This is the first case. The second situation. If the first end of the equation contains the excitation ft and its derivatives, first we choose a new variable y1t. The response of the system with only the excitation signal ft at the right end of the equation. We take delta t into the original equation and use h1t to replace y1t in the original equation. In this case, the process of solving h1t is the same as that in the first case. In the second step, we should consider the linear and differential characteristic of LTI system. In the first module, we have introduced this to you. when the right end of the equation contains the excitation equation ft and its derivatives. The expression of ht corresponding to the output of the system is given by the formula at the bottom. It can be seen that ht is composed of h1t and its derivatives. This is determined by the linear differential characteristics of LTI system. Let's look at this example. The system is a two-order system. We need to calculate ht for impulse response. First, we also choose a new variable h1t. The right end of the equation contains only one delta t. The form of h1t the same as that of homogeneous solution, so it's equal to a1 times e minus t. Add a2 times e minus 3t. Then determine a1 and a2 in h1t. Initial value required since it's the zero-state response. The initial state is 0. That is, the first derivative h1 0 minus equals to h1 0 minus equals 0. The process of finding 0 plus form 0 minus, we have already introduced it in the second lecture. Here, only the solution results are given. The first derivative of h10 is equal to 1. h10 is equal to 0. Take these two results into the h1t expression. We can determine the solution of h1t. From the linear differential characteristic of the system, we can get ht is equal to the first derivative of h1t plus twice h1t. Take the result of h1t into. Finally, the impulse response ht of the system can be obtained. It is given by the following formula. Well, we discussed impulse response. Let's take a look at the step response. Step response is zero-state response generated by the system and action of unit step signal. We use dt to represent it. So this is zero-state response. To further analysis the step response, since excitation signal is a unit step signal, when t is greater than or equals to 0 plus, the right end of the differential equation is not 0. That is, apart from homogeneous solution, the solution also has special solutions. Of course, when solving the step response, we can also use the relationship between step response and impulse response to solve the problem. Later we will have a detailed introduction. The solution process of step response is similar to that of impulse response. We also discussed it in two situations. In the first case, the right end of the equation contains only the excitation ft. What about the different equations satisfied by the step response of the system? This is it. Initial state is 0. It can be seen that, in addition to the highest derivative of gt, the rest are continuous, so there is a value of 0 plus equal to 0 minus equal to 0. In this case, it's from 0 to n minus 1. Just now we analyzed, the solution of step response should include homogeneous solution and special solution. This is a homogeneous solution. After that, are special solution and the form of the whole solution. This is the first situation. The second situation. When the right end of the equation contains excitation ft and its derivatives. Similarly, we need to select a new variable y1t first. According to the method of whole number, we can find g1t first. Then with the linear and differential characteristic of the system, we get the step response gt of the system. In the process of solving ht and gt, we all mentioned that we can use the relationship between them to solve the problem. So let's look at the relationship between ht and gt. Because the LTI system satisfies the differential integral characteristics, the relationship between impulse signal and step signal is differential integral. Then how's that between impulse response and step response? It's also the differential integral relationship. When calculating step response for impulse response, let's pay attention to the limit of integral. A small summary. For different systems at zero state, at the same excitation delta t, the output response ht is different. So impulse response can be used to measure the characteristic of a system. Thus, its solution is very important. It's also the key point of this part. Although when we solve ht and gt in the time domain, which are impulse response and step response, is more complicated than using the transformation domain method. But solving it in time domain is more intuitive, and its physical concept is more clear. That's today's lesson. Thanks.